So if we do this here, again, I created a procedure for this compression of the pad in a solid mechanics problem for the flex model. I've instanced the pad and the platens with a material from the literature. Um, you can find the documentation of that material on the um, links from the original slide. Um, and giving it a neo-Hookean material model that if we look at this neo-Hookean, we support um, being able to provide a if you look at these shear modulus, this is a Poisson ratio about 0.48, but we can even increase the shear mod or the Poisson ratio to the nearly incompressible of 0.49, 0.499. And we have the ability to use pressure stabilization to be able to accurately then solve this problem efficiently. After assigning those materials to different parts of our assembly, um, we can then just move on with defining boundary conditions. Um, I should say with the time stepping method, we're using an implicit dynamic method here. Again, this is a beta functionality, but as you can see, we're using it on a large number of our different problems. Again, this is a generalized alpha with a spectral radius of 0, which gives us an almost quasi-static response. Assigning a boundary condition is then simply assigning symmetry conditions to the pad and to the platens, and then defining a displacement boundary condition on the top pad. Again, those sets are defined in our set manager. I'll color by sets here so we can see those. Just choose some colors for these different sets. Just so we can see that there's those boundary conditions we have for symmetry and the displacement. One thing I want to point out, if we look at any one of these boundary conditions and just tweak, say, a value briefly, I'm going to change the displacement. Instead of being 0, I'll change this to 1. Coreform Flex is based on a principle of wanting to be able to do scripting. And so every command that you can execute through the different GUI entities are echoed commands. And for problems like this, where we want to maybe run different sizes of thread diameters and spacing, different amounts of threads, we really want to be able to do Python scripting or automation of this model setup. And so what we've done for this problem, and I'm going to show shortly the Python scripts to automate this, are copying the commands that are issued by Coreform Flex and then putting those into Python scripts. So for instance, we have this Python script here that builds through Flex commands passing in those strings that were issued by Coreform Flex, which allows for complete automation of the model setup for different pad volume ratios and thread diameters. We'll go into this in a little bit more detail in a little bit. But that's essentially the entire workflow is just to go through and set up all the boundary conditions. We also have contact. So we just have a base contact with friction here that defines, I think, a friction coefficient of 0.3 for a Coulomb friction model. It's just assigned to every surface in this assembly. So I haven't had to go through and choose surfaces for it. It just automatically computes all the surfaces that are in contact. And then we can also probe the reaction forces of this platen. So what I'd like to do now is just show where, if you're interested, you can actually run the Python scripts or the Python script that runs this problem. If you're one of our early adopters, just to see how this works. We have a GitHub repository that has several examples of automation with Python. And we have this direct ink write pad. example. And so what I want to just walk through a little bit is how this is structured. Again, for full automation, we can run this top level Python script that has several test cases that have been pre-set up. You can choose which test you want to run. And then all that happens is that for a given test is we can run Coreform Qubit that creates the geometry and assigns those sets, and then it runs Coreform Flex. So Coreform Qubit is our traditional meshing software that also has capability for geometry creation and modification. So the commands that run or that generate this uh, model are then all of these Qubit commands. Qubit supports a very robust Python API that's able to then create our geometry and assign all of our side sets. And so if you're interested, I recommend reading through or investigating this Python script to see how we create this geometry. But it creates the offset layers for the threads as well as the platens themselves and the full pad. And then building the flex commands um, again through using the flex Python API to pass in all of those commands via strings. And at the very end, we even then fit our data, the reaction force data, with some Python tools that fit that. And so the point of this overall example is to show how Coreform Flex and Coreform Qubit can be integrated within your existing Python-based automation workflows due to their Python APIs that support that. And so if you have questions, you can leave questions on the GitHub repository. We'll our GitHub organization is Coreform LLC, and this Flex Python examples is the repository that contains this. But then we actually ran this simplified model. I only ran it just for speed. They ran this this morning. I just ran it to about 70% of the desired compression. But we can play this just so you can see that we have the contact between these different individual threads. And again, using peer review to do the visualization of this simulation.